Here on Earth, it might not matter if your wristwatch runs a few seconds slow, but crucial spacecraft functions need accuracy down to 1 billionth of a second or less. Navigating with GPS, for example, relies on precise timing signals from satellites to pinpoint locations. Three teams at NASA's Goddard Space Flight Center in Greenbelt, Maryland, are at work to push timekeeping for space exploration to new levels of precision. These advancements are set to make their mark in the field of space-based platforms. One team employs the technique of clock synchronization in space-based platforms to enable telescopes to function as one enormous observatory. Imagine a network of telescopes spread across space, all synchronized to the same exact time. This synchronization allows them to combine their data as if they were a single, ultra-large telescope, vastly improving the resolution and sensitivity of space observations. Another team focuses on developing new, innovative technologies like quantum and optical communications that could revolutionize how we send and receive data in space. These advancements will make it possible to maintain accuracy and synchronization over incredibly long distances, which is essential for deep space missions and interplanetary exploration. The third team is developing an atomic clock for spacecraft based on strontium, a metallic chemical element, to enable scientific observations not possible with current technology. Strontium clocks are known for their exceptional stability and accuracy, which could open the door to new kinds of experiments and measurements in space. The need for increasingly accurate timekeeping is why the teams at NASA Goddard, supported by the Center's Internal Research and Development Program, hone clock precision and synchronization. Their work is pushing the boundaries of what is possible, ensuring that future space missions have the critical timing accuracy they need to succeed. These technological leaps will not only support current missions, but could pave the way for new types of scientific inquiries and discoveries. With each second accounted for, the possibilities of space exploration are expanding, promising a future filled with unprecedented insights into our universe. When it comes to astronomy, the usual rule of thumb is the bigger the telescope, the better its imagery. Guanyang, an optical physicist at NASA Goddard, is working on turning that rule on its head. If we could hypothetically have a telescope as big as Earth, we would have incredibly high-resolution images of space. But that's obviously not practical, said Yang. What we can do, however, is have multiple telescopes in various locations and have each telescope record the signal with high time precision. Then we can stitch their observations together and produce an ultra-high-res image. This technique is known as Very Long Baseline Interferometry, or VLBI. The concept is simple yet revolutionary. Link together the observations of a network of smaller telescopes to mimic the power of a larger one. For VLEI to produce a whole greater than the sum of its parts, the telescopes need high-precision clocks. Each telescope records data alongside timestamps of when the data was collected. High-powered computers then assemble all the data into one complete observation with greater detail than any of the individual telescopes could achieve on its own. This is the same technique behind the Event Horizon Telescope's network of observatories that produced the first image of a black hole at the center of our galaxy. Yan's team is not stopping at Earth-based telescopes. They are developing clock technology that could be useful for space missions, unlocking new frontiers of astronomical discovery. By extending VLEI beyond our atmosphere, this technology could one day allow us to explore the universe with unprecedented clarity, offering a glimpse into the deepest mysteries of space. The journey from synchronizing clocks on Earth to linking telescopes across space represents an exciting leap forward in our quest to understand the cosmos. Spacecraft navigation systems currently rely on onboard atomic clocks to obtain the most accurate time possible. Holly Leopardi, a physicist at NASA Goddard, is researching optical atomic clocks, a more precise type of atomic clock. While optical atomic clocks exist in laboratory settings, Leopardi and her team seek to develop a spacecraft-ready version that will provide more precision. The team works on OASIC, which stands for Optical Atomic Strontium Ion Clock. While current spacecraft utilize microwave frequencies, OASIC uses optical frequencies. Optical frequencies oscillate much faster than microwave frequencies, so we can have a much finer resolution of counts and more precise timekeeping, Leopardi said. The OASIC technology is about 100 times more precise than the previous state-of-the-art in spacecraft atomic clocks. The enhanced accuracy could enable new types of science that were not previously possible. When you use these ultra-high precision clocks, you can start looking at the fundamental physics changes that occur in space, Leopardi said, and that can help us better understand the mechanisms of our universe. The timekeeping technologies unlocked by these teams could enable new discoveries in our solar system and beyond. Clock synchronization is fundamental to numerous societal functions such as power grid management, stock market openings, and financial transactions, according to Alejandro Rodriguez Perez, a researcher at NASA Goddard. Notably, NASA relies on synchronized clocks to determine spacecraft positions and set navigation parameters. One might expect that two clocks, once synchronized, will remain perfectly in sync. However, over time, especially on spacecraft traveling at high speeds, they tend to drift apart. To address this, Rodriguez Perez is working on a revolutionary method involving quantum technology to achieve and maintain precise synchronization. Quantum physics introduces the concept of entanglement, where two particles behave as a single entity occupying two states simultaneously. By applying quantum protocols to entangled photons, scientists could synchronize clocks over vast distances with unprecedented accuracy and security. Central to this approach is spontaneous parametric downconversion, a process wherein one photon splits into two. By measuring when these new photons appear, detectors can use mathematical algorithms to ascertain the time offset between them, thereby synchronizing the clocks. Current synchronization relies heavily on GPS, but this quantum protocol offers a promising alternative for locations lacking GPS access, such as the moon or the far reaches of space.